Hi everyone. Today we are going to move into chapter 6 and we're going to get introduced to what we call chemical kinetics. In this chapter we are going to look at how rates of reactions vary and be able to identify some of the factors that affect the rate of a reaction. We're going to describe how the rates of disappearance of a reactant and the appearance of a product are related to stoichiometry, which we learned in grade 11. We're going to explain how the rate of a reaction is determined by a series of elementary steps that make up the reaction and begin to have an understanding of what a reaction mechanism is, along with looking at how we can use the collision theory to help explain why reaction rates increase or decrease under certain conditions. All right, so today though, we want to introduce the topic of reaction rates. So chemical kinetics is what we're going to be introduced in this chapter, is a branch of chemistry that is concerned with the rates of chemical reactions. So we know that a rate is defined as a change in a measurable quantity that takes place over time. Thus, a reaction rate, we tend to measure the concentration change of either the reactant or a product per unit time. Most often the times are going to be in seconds or minutes. So what we study here is the speed at which the reaction occurs. How fast is a reactant being used up, or how quickly a product is being formed. So how would we determine that reaction rate? We will always express it in the terms of concentration. Our units for concentration are moles per liter, and then we determine the time either in seconds or minutes. So by definition then, the average reaction rate is equal to the change in concentration over the change in time. So that gives us our formula here. A little bit of a typo here. It should actually be a little r, not a big R. Okay, so little r is equal to the rate. That's the variable that we use. And C represents concentration in moles per liter, and T can either be in seconds or minutes, is usually the unit of time used. So let's take a look at our first example to use this particular formula. So it tells us that the overall rate of reaction of production of nitrogen dioxide goes from 0.32 moles per liter to 0.8 moles per liter in 3 minutes. So what pieces of information have we been given? We're given the initial concentration at the start, which is 0.32 moles per liter, and we're given the final concentration to be 0.8 moles per liter. We're also told that it takes 3 minutes for this to take place. Okay, so we wish to find the overall rate of this reaction. So that is what I'm looking for, little r. So the rate then is equal to the change in concentration over the change in time. So don't forget, delta T is equal to T2 minus T1. All right, so that is something that needs to be remembered, that this is T2, C2 minus C1 is how we get this particular value. So we're going to plug in our numbers then. 0.8 moles per liter minus our 0.32 moles per liter over the change in time, which is 3 minutes. Plugging this all into our calculator, we get a rate of 0.16 moles per liter minutes. So therefore, the overall rate of production is going to be sorry guys, a bit of a glitch there. I had to plug in my device. It was starting to have low battery. So I'm good now. So the overall rate of production of nitrogen dioxide is 0.16 moles per liter minutes. So pretty straightforward. All right, let's take a look at another example. All right, so in this one, we're told that the minutes are 1 minute to 4 minutes, and the concentration is 3.5 and 6.2. So it's very important just to be able to extrapolate the information that we're given. We're given the 2 times, in time 1, which is equal to 1 minute. T2 equals 4 minutes. Then we're given the initial concentration at 3.5 moles per liter. And the second concentration is at 6.2 moles per liter. And we wish to find the rate is what I'm looking for. So once again, we're going to plug in our formula. Rate equals the change in concentration over the change in time. Plugging in our values, C2 minus C1 in our numerator, and then in our denominator we got 4 minutes minus 1 minute. Solving, and we get an answer of 0.90 moles per liter minute. Okay, so the average rate of production then in the original question of ammonia for this particular reaction is 0.90 moles per liter minute. Okay, so now we need to do a quick little review of the difference between average versus instantaneous reaction rates within a reaction. We know that the average rate of reaction is the speed at which a reaction proceeds over a period of time. All right, so we're usually going to measure this with respect to either a reactant or a product within a particular reaction over a given period of time. So if we take a look at this particular graph here, we see that we are looking at the concentration of chlorine. So it's with respect to the chlorine gas as time goes on. So it is a reactant, which means it's being used up. So therefore its concentration should decrease as it goes down or fall. It is producing a negative slope. Now, in order to determine the average rate of this line, we need to take the slope of this curve. And so we take the slope of the secant. All right, we choose 2 points on the curve, draw a straight line, and then calculate the slope. All right, between those 2 lines. This represents the average rate of reaction. Now, to determine the instantaneous rate of a reaction, the rate of a chemical reaction at a single point in time, it is going to equal the slope of the curve at a particular point. And we do this by finding the tangent of the curve. All right, so we can do that at any point within the curve. So if I look at the first point at T1, and I take the tangent of that line, we'll notice that the slope here is quite steep. And so that indicates to us that it's rapidly being used up, all right, because it's got such a steeper slope. You'll notice as time goes on, the slope of my curve is smaller. Hence, the reaction rate has started to slow down. Not as much of the reactant is being used up. So as time proceeds, the concentration decreases in terms of how quickly it's being used up. All right, so it's different at different points within the curve. Now, slope tells us a couple different things. We have to know how to interpret the slope and the positive, negative rate values. So if we're going to plot the data for the concentration of a product against time, the result of the curve is going to be the opposite of the one that we just saw. For concentration, it is increasing, so the curve is going to be positive, an increasing slope. If we're plotting concentration of a reactant over time, the graph is going to be falling, all right? And so it's going to produce a negative slope. So this is very, very important to be able to read the graphs correctly and be able to determine what exactly we are measuring. So a negative sign, this is really, really important here. A negative sign indicates a rate of consumption of a reactant, and a positive sign represents the rate of production of a product. Both values can be absolute, all right, but the sign indicates to us if it's going to be consumed or produced. All right, so it's going to give us two different pieces of information. All right, so let's take a look at these particular examples. So if we look at the reaction rate of methane plus chlorine to produce our CH3Cl and our CHCl. All right, so if we can express the rate of a reaction based on any one of these reactants or products. So if I'm going to express it with respect to the reactants, it's always going to be represented as a change in the concentration of methane gas over the change in time. It is going to produce a negative value because it is being consumed. Or we can also express it with the consumption of chlorine gas as well. So it too is a negative value. So it's going to be with the change in concentration of chlorine gas over time. Or we can also express this reaction rate with respect to the production of products, which is going to give us a positive value. So it's the change in the concentration of CH3Cl over time. Or it can also be described with respect to the production of the change in HCl over time. Okay, so now remember, whenever we use square brackets around a formula, it's referring to concentration. All right, so that is an important thing to remember from grade 11. All right, the brackets mean concentration. So square brackets means concentration, and the units of concentration are moles per liter. So that's something to remember. So we can calculate the rates with respect to stoichiometric relationships or mole ratios. So if we know the balanced chemical equation and we know the rate of one of the reactants or products, we can determine the rate of the other reactants and products based on that value. Okay, so we're told in this particular question that the rate of consumption of iodate ion IO3 negative 1, the rate here is equal to 3.0 times 10 to the negative 5 moles per liter per second. So that's the piece of information that we are given. And we need to determine the rate of reaction of all the other reactants and products within this reaction. So we're given this piece of information. The rate of the iodate ion is 3.0 times 10 to the negative 5 moles per liter per second. We wish to find the rate of the iodine ion, rate of the hydrogen ion, the rate of iodine, and the rate of H2O. Okay, so we want to look at all of them. Generally speaking, we can describe this reaction with the mole ratio as the following. We can say the rate of any one of the reactants or product is equal to the required moles, which we get from the balanced equation, what I'm looking for, over the given moles. Okay, this is sort of our converting factor, times the rate that is given. All right, and that's given in the question. So let's use this formula to solve for each of them. So let's take a look at the rate of reaction of the iodine ion, I negative 1. In the balanced equation here, I've got 5 moles of the iodine ion over 1 mole of the iodate ion. This I get from my balanced equation. I'm also given the rate, which is 3.0 times 10 to the negative 5 moles per liter per second. And so when I work that all out, I get an answer of, and because we're dealing with the consumption of the reactant, the value is negative. So I know to put that as a negative, so it gives me 1.5 times 10 to the negative 4 moles per liter per second. Okay, now in my balanced equation, I can also now find the rates of the rest of them. Okay, so I can now find the rate of H plus using the same equation. This time the mole ratio is 6 moles of H plus over 1 mole of iodate times 3.0 times 10 to the negative 5 moles per liter per second. When I work that number out, again, it's a reactant, so it's being consumed, so my rate is negative. So it's negative 1.8 times 10 to the negative 4 moles per liter per second. And lastly, if I'm looking at the last two that I need to find, I notice that they have the same mole ratio of 3 moles of iodine and water. So both numbers are going to be numerically equal. So I am going to write here that the rate of H2O is going to equal the rate of iodine as well. And they're going to be exactly the same, which is 3 moles over 1 mole times, so we're dividing that, folks. I can't put it in here because I've run out of space. but hopefully you get the idea of what I'm doing here. Moles per liter per second. And I multiply that and divide by 1, and I get an answer of it's positive because it's being produced, so it's a positive value, and it's 9 times 10 to the negative 5 moles per liter per second. All right, so if you're given the rate and you're given a balanced chemical equation, using our stoichiometric relationships, we can determine the rate of reaction of all the other reactants and products. All right, so looking at a second example here, doing the exact same thing. All right, so we're looking at the question here. We're given the rate of production of ammonia to be 4.0 times 10 to the negative 3 moles per liter per second. We wish to find the rate of consumption of the two reactants. So therefore, to find the rate of reaction of nitrogen, okay, it's going to equal the change in concentration of nitrogen is what I'm looking for. This is another way to actually write it. And that's going to be, if we look at our ratio, nitrogen is 1 mole of nitrogen over 2 moles of ammonia from the balanced equation times the rate that's been given, which is 4.0 times 10 to the negative 3 moles per liter per second. And when I work that out here, I get a negative value because it's being consumed or used up. So it gives me 2 times 10 to the negative 3 moles per liter per second for nitrogen. And we do the exact same thing for hydrogen to find its rate. And so we've got 3 moles from the balanced equation of hydrogen over the 2 moles of ammonia. And we're going to multiply it by the rate that we know, which is 4 times 10 to the negative 3 moles per liter per second for ammonia production. And when I work it out, once again, I'm going to include my negative because it is the reactant that's being consumed. And it equals 6 times 10 to the negative 3 moles per liter per second. Okay, moles per liter per second. Sorry, I'm putting that in the wrong spot there. And let me fix that here too. Didn't draw it in the right spot. Let's put that all in the right, it's in the denominator. Okay, and that gives us our final answer. All right, so homework, folks, is read 6.1 and answer on page 360, numbers 1 and 2, and on page 361, questions 3 to 5 to practice calculating these rates. And one other thing that I'd like you also to do is to read and summarize section 6.2, which discusses some of the factors that affect the rate of the reaction. So I'd like you to make your own note. This should be a review from some of your previous science classes. And then I would like you to try some of the homework questions on page 365, 1 to 5 for reinforcement. Okay, so I've sort of simplified some of the questions that you need to do here. But it is the expectation for you to complete both of these sections before the next lesson. All right, good luck, and we'll see you in the next lesson.